So today we are very happy to have Markus Oberthaler with us here. He is from University of Heidelberg, where he is a professor and chair for experimental physics. Before he led a research group at the University of Constance with the Emmy Noether funding, and he was also research fellow at University of Oxford. His PhD and studies he finished at the University of Innsbruck. Among the grants and prizes he got is an ERC Advanced Grant, the Emmy Noether Fellowship I mentioned, a European Optical Prize from the European Optical Society, and the Prize for Fundamental Research of the Federal State of Baden-Württemberg. And his research interests in general concern many body systems, and he is using atomic systems to look, I would say, at a broad range of different topics, looking also for quantum effects where one is normally maybe not expecting them in the first place. As we will also see in his talk, he's giving quantum technology from oceanography to cosmology. So please welcome Markus.
Thank you very much. Thank you very much for this kind introduction. There will be no quantum in oceanography. I apologize. But it will be quantum technology which allows people to do something in oceanography which they couldn't do before. And cosmology, there will be a little bit of quantum in there. And I already apologize to people in my field. Today I thought it's more entertaining, and I talk about things you might not have heard at all before, which is the oceanography part. And I will give some aspect of the cosmological things we have done in recent years, which is more in the direction of many particle quantum dynamics in the lab. Okay, so that's the topic. Yeah? And if you look at these pictures, they are kind of frightening. If you look at this of the universe, I mean, it's full of structure. There's lots of things happening where stars are formed and then galaxies are formed. There's even the microwave background, and there's the Big Bang. And here it is the ocean, and the ocean has lots of different compartments, and they are going even down. I cut this off. This highly complex system where you can ask many different questions. It's actually a big dream to hope, or actually a big hope, I guess, to understand all the essentials in this system. And reducing the essentials is a big question. Also here, the cosmology question is also, what are essentials? And it's clear that we are not doing this at all. All we can do is we can contribute a little bit to certain aspects, either kind of inspired by cosmology or by technology, giving people who really study oceans, to give them new handles or new tools to look at certain questions they had before, and which we can also resolve. And this is actually where quantum technology helps. And it's not defined by quantum technology per se, it's defined by technology which helps other people doing something they couldn't do before. Okay, so if you want to put this in this kind of classical kind of quantum flagship framework, these logos, some people might call this quantum simulation, what we do, but I call it basic science inspired by questions from cosmology. It's not what we do. We don't do cosmology, but we do certain questions. For example, what happens if you have a very dense quark-gluon plasma in early times? How does it develop? Or we ask, what happens if you have a scalar quantum field on a curved background which changes in time? This is not what you have in cosmology. There's much more happening, but there's certain aspects of it. Okay, and now on the other side, the ocean, this is very easy. That's really now a technology where we do sensing at the quantum level, and what quantum means will become clear in a second, which helps then to say something about questions in the ocean, and especially to say something about, actually, why does this not work? Say something about the CO2 content of the water in the ocean, how much of anthropogenic CO2 is in there. This sounds like an important question because you would like to know what is the sink, actually what was the sink in the past, and what is stored in the ocean, because this will come out at a certain time when the water gets up again. Okay, so what we take is the basic ingredients are already kind of got Nobel Prizes, awards for that. That's laser cooling, that old, but all of us use it, at least in the atomic physics case, for preparing states, which we then further go into the quantum degeneracy. But here we will stay at the cooling level, trapping atoms with light. And what we will do using that for doing trace analysis, but trace analysis not on densities, but on single particle level. So we count particles one by one, and that's the level of concentration we have to look for if you want to do something interesting for environmental physics, more specifically to dating water, ice, or ocean water. Okay, the second Nobel Prize is this kind of how you generate then a many particle quantum state, very reproducible. And then out of that, we ask questions about, is there, if you have an isolated quantum system and you hit it hard, you go far from equilibrium, is there a dynamics which you can hope to understand? In all its details, it will be very complicated, but in certain cases, this becomes extremely simple. And simple means you can describe it as universal, i.e. you need only few numbers to explain the dynamics you see. And it only happens if the dynamics is special. And this is something you can ask. This was asked first in heavy ion collisions. This should exist with an ON model. And this is something we addressed with our experimental system if we can really see this kind of scaling behavior, what's expected there. And the latest news is how that we can generate also this, use these quantum gases to generate situations where we have a quantum field on a curved space-time. And it's very different. I will show you. We are not dealing with single particles in this context, but we are always in this limit of having many particles. And the field description, i.e. a number, or maybe three numbers, is a good description of the whole system. These numbers are not classical numbers. They are still quantum. There are correlations and fluctuations on top of it. But that's the regime we are working in. Okay, so now let's start with the left side, with the ocean. So this is the problem, and the problem posed is, well, you want to take here water out, and then you would like to understand how much CO2 is in there, which was produced by human mankind, assuming that human mankind mainly produced it in last 150 years. Okay, and CO2 has not a label saying I'm that old. So essentially, what you ask is, can we get an information about taking a sample out here? Can we say something like, what's the kind of average time the water needed to get from the surface to this point? And this can be very complicated. It's not like a parcel which moves from one side to the other. It's about diffusion and convection. At the end, you have a mixture, and then this is something you want to address. Overall, this is a very complicated picture, so I would like to reduce it to essentials for me. It's ocean, that's water, okay? And then you have this water has no structure, and there's a boat on top of it that we're going to need in order to get samples from the water. And what this boat allows us to do is it allows us to get water samples out of a certain depth. Okay, now if you take this water out and it would be not structured, then it would be very boring. It would be no need to go down if it's all the same. You just take it to the surface. But obviously it's different because you can make these compartments and you don't separate it in parts. It's like densities. Certain are old, others are very old, and some are young. Now, this is a kind of a classification we use for all of us. It's relatively clear because we have birth and death at the boundaries, and we know what old means. It's closer to death, and young means it's closer to birth. Now, here we have to define what it means. So we need a reference, and our reference is now assuming, knowing that 25% of the contemporarily produced CO2 is stored in the ocean. We are asking about anthropogenic CO2. That's the timescale we are interested in. Yeah? So last 150 years would be kind of everything younger than that we would call young, and everything older than that we call old, because it's not relevant. Okay, so now how do we go about this? Now this project started about 10 to 12 years ago in Heidelberg, and this was together with Werner Eschbach. And Werner Eschbach, he's actually a groundwater guy, works in groundwater environmental systems. And he actually gave me this transparency. I use it still. And still there's the same question. What is old? Old here is, this is extremely slow sometimes. Old is the water gets respiration, get raining down here, and then it goes in the ground. And then you ask, how long did it take from being at the atmosphere and then getting out here from the well to get the cow some water? Okay, that's the age of the water. Here it's much easier to think about parcels produced. It depends on the aquifer, how it's flowing, if there's also diffusion. But here you can have more the parcel idea that the water sinks down and then as a more or less bucket gets out in the well sometime later. Okay, so how do we do this? All you need is a tracer. And for age, we know C14 method is a good tracer for age because it decays and we know it's produced. We know the production rate, and we know it's only uptaken by beings when they're alive and when they are alive. And if they died and they don't do it, and then just the C14 concentration decays because of radioactive decay. The similar thing is also here possible, and it's called Argon 39. This is the isotope which is interesting, and this is produced in the upper atmosphere by cosmic rays and nuclear spallation. And if it's produced, then it's also dissolved in the water. And in the water, then it just sinks down here. And all you have to measure is the concentration of Argon 39 here at this point, because at this point, at the top here, you can measure any time, you know, the concentration. It's relatively constant. Okay. The good thing about this is that it's 269 years is the decay, the half-life. That's perfect. That is exactly the time scale we were interested in for the anthropogenic CO2 production. So that's actually a good thing. So if it decays to half, we know it's 270 years approximately old, or has taken that time to get there. The other small print is hidden, but I show you now, is the abundance. The atmospheric abundance of Argon 39 is not large. Yeah? And it's a number which is 8 times 10 to the minus 16. And in the following, I will call this approximately 10 to the minus 15. Okay. So everything I tell you is a little bit more extreme in reality. So 10 to the minus 15 is the concentration. And this is a number which is something which is a large number or small number. If you take the reverse, it's large. And for femtosecond people, this is in meantime also long compared to Atto. But still, it's a great number. It's a strange number. And I would like to give you a perspective of it. So we started with this cosmology picture and oceanography. So if you take cosmology and you ask what's a large number, then it's the age of the universe, right? So 13.7 billion years. And if you calculate this in minutes and ask what's 10 to the 15, then it's about 7 minutes. And if you take 0.8 times 10 to the minus 15, then it's about 5.5 minutes. So 5 minutes on the day of the duration of the universe, that's the concentration. Now, this is a very strange number. It's just taken out because I started with cosmology, and it does not give us a hint what it really means. Okay. Now, another thing sometimes you say is if you can buy it, you understand much more what you have. And so I tell you can buy this concentration. If you go and buy this kind of globally, you buy D15, you buy the same concentration. Okay. This also does not tell you much. You may have heard maybe jokes about it, but it doesn't tell you how big this number or small number this is. Okay, so now there is a good number which is everybody can relate to, and that's money. Money we can relate quite nicely. We have it in our pocket. We know what it means to have 100 euros. That's definitely a small number compared to the number I'm talking about here. But if you think about the public debt of Germany, which is 2,390 billion euros, currently rising for many years sinking, that's a large number. This is 2 times 10 to the 12 euros. It's not that you typically call it 10 to the 12 euros, but it's lots. Okay, so now 10 to the 12 is still not 10 to the 15, so we can make sense out of it. This gives us a factor of 2, a factor of 2 orders of magnitude. So we have 10 to the 14 cents. So how much is 10 to the 14 cents? So the depth of Germany, it's a cent. You put it in a drain, you fill the wagon, and then you ask how long is the drain, and you find it's about 2 times around the Earth. Okay, so this is lots of money. Yeah, but still it's 1 order of magnitude too small for what we are talking about. Okay, so now let's take the drain 20 times around the Earth and take our concentration. And remember, you can buy it. Yeah, you take our concentration, and 1 cent is green. And that's the challenge. You have to find the green cent. If you find the green cent, you have no information, because what you want to measure is the decay of these objects. So you need statistics. You take 100, and if you find 50, then you know it's about 269 years old. Okay, so this is a challenge, and see, it's like it's crazy numbers. It's like you have lots of particles, and you have to select very few of them, and then do from them you can extract information about what you're interested in this case, the age of water. Okay, so now how do you see different scents here? And obviously you see the color is different. And we know that the color has to be different if it's now atoms, because they have a spectrum which depends on the mass of the nucleus. And so you have the isotope shift. And the isotope shift here is about 500 megahertz here between argon 40, which is the most abundant one, and argon 39. And if you look at this, it's clear you can distinguish. Red is red and blue is blue, and there's lines. No question they can distinguish it. And if you're a little bit more precise, we would say what you have here is really a line width of this line. And it already says up here what is the important message here. The power law is not exponential, because this is the natural line width here. And this decays with 1 over delta squared. It's a power law. And a power law is sometimes nice, but sometimes not. In this case, not, because it means as nice as it looks up here to be separated, if you look here, the suppression is just about 2.5 orders of magnitude. Okay, and 2.5 orders of magnitude on the scale of 10 to the 15 is nothing. It's not useful. Okay, one can plot this. If you take this now, this absorption spectrum, and say you take a gas out of the ocean, you degas the water and get the gas, and do spectroscopy, then this is a kind of what you would calculate, what you get as an absorption signal. You get argon 39 here with 10 to the minus 15 probability, but you have a 10 to the minus 5 probability to get it for argon 36, say, but this is way much more than 39. So if you do spectroscopy, what you would see is all the other isotopes, because there's so many. Okay, so now what's the way out? So this is single particle, this is like spectroscopy, i.e. a photon scatters from an atom. Suppose we would have a process where we don't have a process which depends only on 1 absorption, but on 2, then it would be already squared, the probability. Okay. So now if we take 8 photon process, then you would say, 8 photon processes, you can distinguish argon 40 from argon 39. It's a power law to a certain factor is already very small. The only thing you need now is an 8 photon process. Okay. This is not so easy. But there was a very smart idea by Zhengtan Lu in 1999. Actually, 100 photons too. The more you take, the better it gets. And Zhengtan had a very nice idea. And he said, like, I don't know if he said it, but the result was absorption of an atom with a single photon. This is one process. But what you always get with it is a kick. So essentially, if you then couple your spectroscopy signal with motional degrees of freedom, you might be better off, because if you have a fast atom and slow it down, you need lots of photons to be scattered to reach an atom which is at rest. So getting here means a higher order process of photons, a high number of photons scattered to get the particles decelerated. Okay, and this was his idea. He's now in Hefei since 2015, I guess. And there he built up, like, I think 7 machines of what I'm going to tell you. So he does this now on standard call, argon krypton 81, which is an isotope which has 200,000 years half-life, which is for much older life, older times, older water or ice. And he also now has an argon machine, as I will tell you what we have. Okay, so the idea is, and I don't have to explain this here very long, a photon meets an atom, it gets absorbed, the atom gets a kick, okay, and it emits again, it gets a kick. And we know that if you want to have an atom decelerated, it takes lots of them, and you scatter, and then you get accelerations, which are crazy. But you have to scatter many photons in order to get it slow. And this is the kind of new, nowadays, maybe interesting picture of a green jet, like decelerated by red balls. Not a political statement. And what you can do here is you can stop the atoms, but stopping them means you have to scatter many photons resonantly. And you can look at the atoms because they scatter photons. And that means you can count the atoms one by one because you see them fluorescent. And here I'm in the mecca of single particle detection. They can be spatially resolved. In lattices, this is now really just a very simple thing in a mod single particle, and you count them. They're just rare. Okay, so this is what it looks like. It's a machine, a standard, like standard technology, like flying to the moon technology, but you have to tweak it in order to get a high flux throughput, to have at least at the end some atoms you can count, because you have to send 10 to the 15 atoms through, and you see one. Okay, so what you do is you take lots of light, i.e. transverse collimation, cooling, deceleration, trapping, and at the end, you're maybe lucky and you see this kind of blob, and this blob is a single argon-39 atom in this trap, and you can then just detect it and say, here's one. And now you do this and ask how many is in a sample. The typical count rate what we get is 7 per hour, which is consistent with what kind of throughputs you can make by having bumps enough that you get the other atoms away. That's about the number. So you have to always do it for 24 hours to get good enough statistics to make a statement about other 7 atoms for an atmospheric. This is called modern argon, so atmospheric sample. If you have another one which is older, then you have to obviously measure longer in order to get the same statistics. Okay, so now what can you do with it? And now comes the part I'm not participating, but enjoying seeing the pictures, and sometimes I'm envy. These are my colleagues in environmental physics. They get the samples, and they go to nice places, and there are lots of them, and this is one. This was not chosen this way, but this is a Cape Verde island, and you see the sunset. And if you go in this direction 500 kilometers down the sea to the south, I don't know where south here is. Anyway, south, south. Then there is an interesting area, which is indicated by the stars. And this was indicated to us by people from GeoMar, saying there is a very interesting situation, 400 meters depth, where there's not enough oxygen. There's an oxygen minimum zone in the ocean. And they want to know if they have a proper estimation of the age. How long is it there, this minimum zone? And their estimation was about 100 years. So it was the right ballpark for us to say, well, we check it. We can do it. This was our first project actually in the ocean. Okay, so they went there, got the samples, and do this by this boat. The boat is called Meteor. This is from GeoMar, a research vessel. They took out not only one volume, but many of them. And then this looks like in reality like this. Then this is what you send down. This is called Niskin bottles. These are just 20-liter bottles. You close down as you go down. Then you get certain volume out of the ocean. And actually, the challenge is that this actually going down to 4,000 meters, that's the depth there, takes about 4 hours. So it's time-consuming going up and down, getting these vessels filled. And our big step was that we could do this now with 20 liters of water. We can do this dating. This means like we can have a machine which has small enough volume of gas, which is about 1 milliliter of argon, to be enough to be measurable. Okay, at the end, what we get out of these bottles is bottles, and these are methane bottles. This is the cheapest version of a container, which is tight. And then the water is filled in there on the boat. We get these compartments, these kind of gas bottles. We degas the water by shaking it and just doing degassing by a vacuum pump. And then at the end, what we get in our lab is a thing like this, where there's a cold finger in there, charcoal, and there argon is bound. So this is compared to the nice beach, actually reduced to not the essentials, but for us, the essentials is the gas in there. And this gas, then we plug onto our machine with the input, and then we run the machine and count. And then what you get out of that is a graph like this. So here you see the argon concentration, and I make it translated. So 50% is 269 years, and 70% is 138 years, and this is 460 years. And then you get this as a function of depth. Here you can get these count rates. Okay, and that tells you how old is the water. At the surface, you hope it's 100%. Yeah, that's good. That's a reference point. That's 100%. Then you see lots of data points here where we measured at this 400-meter depth, because that was the interesting area, and it was about 100 years. So we confirmed what they knew, somehow good. But actually, this was not the big surprise, and this was not what excited us most. It was like if you went in further down, and essentially the age got older and older, but then it got about to 400 years, which is also somehow expected. But what was not expected is this very special area here. Here it turned out to be younger than expected, or estimated before, because you don't measure that. Yeah, at the moment it was always estimation via very rare tracers, like CFCs, for example. And then you ask if it diffuses in there, you can say something, make an estimation. What's kind of what's the bound on the age you can make? Okay, so what we found there is that the age of the water was younger, and that means in this area here, that means that in this area here, specific to this very special spot in the ocean, it's about 40% more anthropogenic CO2 in there than assumed so far. That sounds like not a small number, okay? But now you have this kind of, this is a volume, which is also not small, but there is much more because you go to 4,000 meter depth. And you can ask, what's the whole column kind of now? What kind of CO2 is in there more than what was expected before? And that's only 10%, okay? So now at least there's something you can say, you didn't know this before. It's not yet a result which is relevant somehow, because if you know it on one spot in the ocean and it's so specific, it could be everywhere different. And you don't know. You might think there are solutions, you know exactly how water is transported in the ocean, at least I thought, but this is not true. If you ask where this water sample comes from, there is no answer. It's also a non-trivial answer. But in this way, here you ask the question you're interested in, namely COT, the age of the water. When was it last time in exchange with the air? So now actually, I don't know what the time is. Is there a time? Okay, and I should stop at 20 past. Okay, okay, good. Yes, if you have argon, then argon is always the same, right? The question is just, do you have somewhere argon which has an interesting information about age, or you want to know the age? And a very interesting thing is ice. Glacier ice is full of bubbles. And actually, diffusion of argon in ice is extremely slow. So essentially, what you have there in this bubble is old air. It's really cool. It's an archive. And you can analyze this air in different ways, chemicals, for example. But typically, you don't know how old this bubble is. Okay. Now, whoever was kind of skiing might have seen these ice caves, which is actually drilled for the people going skiing. But for these people working in glacier science, this is wonderful because they have samples. You see stratigraphy, say like these kind of lines, which gives you some information that this should be younger than this one here. And you can take ice by just a chainsaw. You just mill it out with a chainsaw and analyze it. And so that's what we did together. And we found out actually that this ice is about 200 to 300 years old in these kind of skiing resorts. This one is in Stubai. You might have been there. But it will be not long there anymore because these caves are actually most likely not there in 10 years anymore because ice melts like hell in the glaciers. And at the moment here, they have put some plastic on top and actually see the cave on top of the whole thing because there you might make sure that the ice is not melting. So this is a big issue. But it's a wonderful archive. Another one is this one here, and I find this impressive. Yeah, this is Jamtal Ferner. It's like, you see like ice started up here. It was a big glacier and it was flowing down here. And you see really like it flows like almost laminar, while here it's kind of turbulent at the side. Yeah, the people, we are here. I was actually there too. There I enjoyed also taking samples. So we were standing here. And what you see here are stripes. And this looks like tree rings. And they are connected to tree rings in the sense that if you have summer, you have dust. In winter, you have snow. In summer, you have dust. In winter, you have snow. So you can count them, and there's 150 of them here if you count them down. And you would say, well, down here, this ice here has to be 150 years older than up here. But it's not true. Because in difference to a tree, which always grows, ice can also melt. So if you have some hot summers in the last 100 years, it might well be that one of these stripes is 3 years worth or 5 years worth. And so if we are now analyzing this, and we're currently doing this, a current project, we're taking samples of the surface of this glacier, and if we can now actually give a stamp on how old it is, and it does not fit with the stripes, we can actually say there was a hot, kind of a warm period where ice was melting. The other thing, which is not so dramatic if you're seeing it here, but if you're on top of it, it's kind of melting like hell. we were there on summer, and it's natural that you have kind of small water things going down, streams going down. But then if you ask how does the ice disappear, and they said it's 1.5 to 2 meters per year. Okay, and this is about 10 to 12 meters deep. So in about 5 years, this is gone. Okay, maybe that we should not care, but if you think about what information is in there climatically, it's very local information. So, but in these bubbles, I find this extremely interesting, and I hope that we get fast enough in our improving our count rate that we can do really a clear statement that these are 150 years worth, or there was some hot summers. We are not yet there. This is a question of statistics. Now, the other thing what brings you to is other places. Lake Kivu is an extremely interesting lake. You might, I don't know if you recognize this volcano. This was kind of last year. It was a big news in May, was erupting. And this is actually not so specific, maybe if you see it, but if you know there's a lake in front of it, maybe also not so. But this lake is a very special lake. It's hotter in the bottom than up there. And the density down there because of salt is higher than up there. So in there in the bottom, there is methane and CO2 stored because it's salt there. And if there's a big eruption, then you form a bubble. If your bubble forms, then you rip out all this gas which is stored in there. And there were already people like in this area, there are other lakes like this, and there were kind of full villages kind of just suffocating because there lots of this material comes out in a very short moment. So having a volcano there and eruptions is a dangerous thing, and that's why one studies this lake very carefully. And we were studying it because it's an extremely interesting lake. It has no convection. It's all kind of in one layers, and we were hoping to see the age of this water. And what we actually found is the same as in this permafrost. It's actually all the argon we measured is more than expected. It's coming from the future. Okay, so there's more argon-39 than in our atmosphere. And the interesting thing is that argon can be produced not only in the upper atmosphere, but also by volcanoes, or in this permafrost case, by the neutrons from the surface bombarding and activating potassium. And this is now a new twist that we use this for seeing these kind of information in environment where the water comes from, if it comes from the volcano or not, could be seen in argon-39. And that's a little bit like how environmental physics works. You have indicators, and then you see something, and then you find out, well, there's much more telling you than age. This is a tracer, which is very interesting features, and it's used by many people. Okay, so this is the part on the technology side, and if you have technology, you would like to build a box and put it somewhere. This is our container where we have an Argon machine in there, which starts running. It's not a container to put somewhere in a box, but it's a container. And it's kind of self-contained, and it's planned to just measure samples for environmental physicists. Okay, so with that, I would like to close this part and come to something more traditional, I would say, which is this basic quantum science questions, but with this kind of background of inspiration from this kind of picture. And the first thing what pops up here, I guess, is the question mark. And we are not looking at the question mark. We're looking a little bit after the question mark. Okay. So we ask about a very specific question, namely, what happens if you have a quark-gluon plasma? So what is a quark-gluon plasma? This is something, a state where already the universe has expanded like crazy, and you have starting producing matter. And this kind of state is also analyzed at CERN. There, they produce lots of single little bangs. We have a big bang, which is singular, but the little bangs, and by having heavy ions colliding with high energies. And the picture, what you have there is, if they collide, what they produce is they produce material of a special kind, namely you have as many particles, antiparticles. They are so high density and temperature, actually temperature, that their quarks are free, and you have gluons and quarks free, and that's why you call it quark-gluon plasma. At a very early phase, you would even say it's what people call plasma. It's just gluons. Yeah? The quarks don't play a role. It's all gluons, and they are bosons, described typically by ON models. It's not the full kind of Monty beautiful kind of standard model, but it's highly reduced to a model of n fields interacting equally, n to infinity, you can calculate something. Okay? Okay, and so for this, one maybe should continue here what happens afterwards, after this collision. This takes about 10 to minus 22 seconds, so it's very short. And then actually 15 orders of magnitude, that's another 15 orders of magnitude. Later, you look what you get out. Okay? And out of this, you would like to understand what happens here before. And it's kind of understandable that maybe you see the hadronization and maybe the kinetic freeze out, all this kind of phenomena which happens as the gas expands. But it's very hard to imagine that you get this kind of initial condition where the gluons are the dominating thing, and you can describe it as an ON model. Okay. Okay, this is now blue. This is from Rick, and since I'm in Heidelberg, I have to show it in orange. This is Alice, a collaboration at CERN, investigating this kind of physics. And this is actually what you get out. You get out this one single shot, what they call one collision, get about 10,000 particles out, and out of that you reconstruct what happened before, or try to reconstruct what happened before. So now we do it differently. We ask, what are questions here asked? Can we detect them? Okay, and what has been found, and this is Jürgen Berges originally, and then Thomas Cosenza also translated this in our community, and he kind of investigated his ON models. So it's a model, it's not kind of the standard model, it's a model, mathematical model where he can do calculations analytically to a certain level. And then he found something. And what he found was that if you have an initial condition far from equilibrium, this is defined by all momenta are highly occupied up to a certain scale, he found that the system develops in time in a peculiar fashion. And in order to have this complicated system kind of represented with one curve, what you plot here is you have a system which fluctuates, okay, and it fluctuates on small scales, it fluctuates on big scales. And what you plot here is somehow the power spectrum of these fluctuations, okay? So large number here, large number here means large fluctuations on large scale, and small numbers here on large K means small fluctuation on small scales. And what he found is that you have a behavior that this kind of distribution here does not change shape in time. It stays the same. This is the two yellow lines. But what it changes is the length scale changes in time and the amplitude changes in time. And they do it in peculiar fashion. Namely, they do it with a power law. What it means is if you multiply the scale for this whatever color this now here is, this right-hand curve here, we multiply this with a certain factor for a certain time t. If you do it at like time t later, you have to multiply this with t to the beta. And beta is the exponent you have to find or to have a prediction for. And there's only one solid prediction in this case, and it was beta should be 1/2. Alpha is a consequence. Alpha is a consequence if what you see here, and you can call this transport because you change momenta. If you transport conserved quantities, then the surface, the area below this curve has to be constant. Okay, so if the integral is constant, it has to go up. And that means alpha is dimension d times beta. It's connected. It doesn't have to be like this. But if you have this situation, then you know you have a conserved quantity found experimentally. And where is the experiment here? The experiment is here. What is the F? The F is what fluctuations are you looking for? Is it on density? Is it on phases? Is it on particle number differences? That's what the challenge is, to find out experimentally what observable does show this behavior. The scaling in K is general. This is kind of a length scale changes. This typically does not matter much what you look for. But if you want to see alpha equals beta, you find this observable. So now this is what we do. Compared to these beautiful experiments here, we have single particles on single sites. In lattices with hopping, we are always in the regime that we don't distinguish single particles, but we take a volume, and in this volume, we have about 200 to 300 particles. Okay, and this is our unit. So this unit you can represent with a vector, because it's like small spins adding up to a big vector. And this is what you might maybe call order parameter. In our case, we call this our field. This is our quantum field. Why quantum? Well, it's built up by small individual spins, and that means this is fluctuating. So this is actually an operator. It's a fluctuating field quantum mechanically, and now you can ask, how do you observe these fluctuations? You would have a very hard time to observe absolute fluctuations. So look on one spot and look for the fluctuation. The whole system typically does this, and you see these fluctuations and not the quantum fluctuations. The very natural thing is to do, and also theoretically, is you don't ask about single position, you have different positions. How are fluctuations correlated between different positions? Give you information of is there quantum in there or not, or generally is information about your system. Okay, so this is what we do. We do spatial correlations of these vectors, but at the end, what we correlate are expectation values locally, but this we can actually estimate quite well. And this operator aspect we get because we do ensemble averages, do many realizations and measure these correlation functions up to fourth order. Fourth order we did in a kind of systematic way. Okay, and with that we characterize our system, and it's also kind of this kind of if we take r prime equals r, you see this is f squared, and f squared are the fluctuations. It's a kind of how does the vector fluctuate? Okay. It's always the connected correlation function. You always subtract the trivial, single particle expectation values. Okay, so this is what we do. And now we need a quench. We need a bang, not a quench. But we do a quench for a bang. Okay, so we do a quantum bang. And what we use there is a system. We have a one-dimensional gas, which has different phases depending on a parameter, which we can adjust by microwave dressing, for example. And we can prepare here states, and what we compare very well is this state out here, polar state it's called. This is actually all the particles in MF equals 0 here in the spin 1 situation. This we can do with high precision, reproducible, and with high fidelity. What we can also do is we can then energy shift this level here, and with that actually we go through this phase diagram, and we can quench this point to this phase where you actually have in the ground state as easy plane ferromagnet. That means this vector here is in a plane orientated in random directions, but it will choose one direction if you then at the end observe it. So spontaneous symmetry breaking at the end. This is a quantum phase transition. That's what we do. And now you can ask, free energy picture, what would you expect if you put this situation? You have initial state prepared at fx and fy equals 0. You have this kind of Mexican head free energy landscape. What happens? And everybody of you most likely would expect rolls down. Actually, will spread out because it's quantum mechanical. It goes all directions the same way. But then for long times, if it thermalizes, you would expect that somehow it settles down here in this trough. And then you might wonder, well, where does the energy go? But the energy goes in the phase windings, which you don't see in this picture. This is not the whole energy. Okay, so you would expect that it settles down in this trough if it thermalizes. Okay, now the good thing is we can look at this directly because we have access to this order parameter with a special technique of imaging, which I'm not explaining now in detail, but it uses the fact that the Hilbert space is larger than f equals 1. There's also f equals 2, and we can estimate the vector fx, fy at one point. And what you see then is what happens in this situation. Indeed, this kind of situation is that the whole system expands, doesn't go one direction, it expands symmetrically. And then after about 14 seconds, which takes a long time scale for these experiments, it took us some while to get somehow control of this heating processes, and how we solved it at the end, we don't know. It was kind of at the end, it worked, and we don't know why, but we are happy. And so if we go for longer time, 42 seconds, then you see it really settles down to this ring. Now you might think, is this thermal or not? Okay, this is now actually somehow a magnetization question. But we have more information, we have the spatial information, and we can analyze this. As I said before, we correlate now spins with each other. We do a Fourier transform of that in order to understand what is their structure, what length scales fluctuates more. And then we get exactly the graph what Jürgen Berges was kind of looking at in this original kind of in this paper here, or in this figure here. And experimentally, it looks like this. This is our data now. Okay, if you look now for different times, you see red times, you have this curve here, which has occupation numbers at a certain length scale, but later time actually goes down, or actually it goes to the left. Okay, so essentially the whole system redistributes the fluctuation from small scales to large scales. And the question now, is it done in a scaling fashion? This you find out by rescaling the functions, and then you get this nice collapse where people are happy to see it because it says the system is self-similar. If you know it at t, you know it for the future too. up to a certain time, because at the very, very final time, it should thermalize. But that's actually beyond our scope of experimental timescales. Okay, so this actually now confirms that this seen that the exponents are not perfectly correlated because it's one-dimensional. But we were very happy with this result, and Jörg Schmidtmeyer published this back-to-back at the same time for 1D both gases. And then later on, this is also connected to turbulence, but this is here the result when you do these quenches and you ask what happens after a quench, you get this kind of scaling behavior. Okay. So now this is a connection, and I know that in our community, the connection between high energy physics and cold gases is interesting, and I fully agree with that. But this is a very funny connection because it's where something, maybe for me, it was at least like this, when I learned kind of high energy physics, for me, collisions and particles coming out. But high energy physics is also about this quark-gluon plasma, which is much more on our side. It's a gas of gluons, which are weakly interacting and have some dynamics. And so this is actually a connection between high energy and cold gases. We actually showed something generated in high energy first time experimentally. So now, 2 minutes for the cosmological part, which is okay. Okay, so if you look at this trumpet, it took me ages to understand what it tells me. And I have to be honest, I thought this is really the boundary of our universe. Yeah? It's not accessible out there. But what it really represents is the metric, how it changes in time. It should be actually drawn inside the whole system. It's everywhere the space is expanding. Okay? And it has a very peculiar behavior. It has a very fast expansion at the very early times, then a deceleration, and then a kind of settling down almost, and then an acceleration, which is kind of scary. Because it accelerates and accelerates. And there will be a big rip at a certain point. And well, okay, we are here, and we will not experience what happens if you have a big rip. But we can ask questions in our systems. And obviously, we cannot do this. This is Einstein's equations. So it looks like one equation, but if you write it out, it's like a long equation. It's nonlinear, and it's not easy to solve at all. So there is one assumption that you assume, and I don't know why, but okay, it's a good assumption. Yeah? You assume the universe is homogeneous and isotropic. So it doesn't matter where you are and in what direction you look at. It doesn't have to be like this, but this is a good assumption. And this actually limits you in what kind of form this metric can have in a very strong fashion. Okay. Now I do everything already 2D because we will work 2D later on and not 3D. And so if you do this assumption, then the line element, which actually connects, is another representation of the metric. The metric gives you a connection between time and space. So it gives you the line element, and it looks like this. So the line element is given by this form, and this is called the Friedmann-Lemaitre-Robertson-Walker metric. This comes out not for solving this equation, but solving, assuming homogeneity and isotropy. That's what it comes out. This is the structure. And what you get is two numbers, actually. You have kappa, which is a measure of curvature, how curved is the space. And you have a scale factor, A of t, which actually says what's your length scale. Yeah? Okay. So this is actually something I learned too, and I'm still learning it. Can have very different kind of coordinates in this business. This is the coordinates where the reduced circumference polar coordinate. That means if you go around the circle, you get 2 pi, which is typically not the case if you have curved space, but in these coordinates you have. Okay, so if you have this, then you would like to have a situation like this. You would like to have a metric, and you want to have some object living on the metric. And ideally, the simplest case is you want to have a scalar field, and you want to have this quantum. Okay, so this is something we would like to implement. The simplest thing, or actually, let's put it the other way. That's the thing we can implement. A scalar field, quantum mechanical, massless, non-interacting on a metric which is adjustable, FLRW form. Okay, so how does this go? The first step is a big step. You go from infinite space to your lab. How does this go? This is actually infinite space, looks like this. So this is negatively curved space. It's a hyperbolic surface going up to infinity. Okay, this is in 2-dimensional, embedded in 3-dimensional. You can plot it like this. So the geodesics is between these points is this line here, and this line you find by solving the geodesics equation, shortest connection. Infinite space, not good for lab. Yeah? So how can we reduce this? Well, there's one way of mapping this infinite space on finite space, Poincaré mapping, where you can map this by making this projection, which has this very special point down here, and you make a linear, each point is kind of connected to this point down there. And then you make, when the surface here is goes through the surface, you make this point putting here. Okay, so you can map this infinite space on finite space, and it comes because it's curved. Okay, what we also see is the lines here, they are equidistant. So how do we define equidistance? You take a bulb, light bulb, because C is constant, and you take a certain time and ask where you are. So this is a light bulb, shine, and it makes these distances. Obviously, this is not in our case true, because speed of light is constant. It would be, the circles would also have a radius which increase linearly as you go along. But this one is closer and closer and closer together. Why is that? Well, it's clear. If you go up here and you take infinite points out there and they move a little bit up in their space with C, then essentially it boils down to this projection of a little bit of a motion. Okay, so now on this kind of finite system, you can, this kind of mapping, you can also write down the metric, which has this form. And it's actually not now obvious to see that this is actually something you can implement. But it's this part here which makes it implementable, which says the scaling factor should have a spatial dependence in a certain form, namely inverted parabola. And whoever works in PCC, inverted parabola sounds like good. The question is just why is the scale factor here connected to inverted parabola? Okay. Now, if we go more concrete, actually, sorry, I'm sorry, I have to go back. I've forgotten that this picture is here because it's beautiful. Yeah. Essentially, what it means is that if you go out here in real space, the distances get larger and larger and larger and larger. Essentially, it takes you infinite time to go around the circle. Yeah. Because the ruler gets smaller and smaller and smaller. Yeah. And this is called hyperbolic geometry, and that's behind the Escher pictures. They are kind of fulfilling this kind of metric, this hyperbolic geometry, that you can have more and more of these kind of objects on the surface. Okay, anyway, so now how do we produce it, and how does this connect here with the experiment? So this is what we have. We have a 2D gas, potassium-39, not argon-39, potassium now. So there's a proton-neutron exchanged. And this is a 2D gas. Now, what is a 2D gas? Yeah, here you have a 2D gas, and you have phonons on top. Say you have sound, and now you ask how does the sound move? Well, the sound moves depending on the stiffness of the system. The stiffness is given by scattering length, so interaction between the particles, and density. That sounds not so bad. If I take my distance definition, take the speed of sound times a constant time, gives you the length scale, then actually this naturally produces produces something like a hyperbolic geometry, because as you go out, the density goes down, the velocity goes down. And it means if you make your bulb experiment, it gets slower and slower and slower and slower. Actually, at the end, it stops because sound velocity is 0. Now, this is a limit which we would say this is not what we can control very well. But there is a certain part in this situation where we can have this dependence of speed of sound, which actually allows us to implement a system which, if you map it onto curved space, and map it on the curved space with constant speed of light. Okay, so now the question is, what field is living on this kind of metric? So if you look about the field in this situation, you would describe it as a classical field, Rossby-Delsky solution, plus a phononic field, or like a Bogolubov field on top. And this is actually a very special part. They do a different decomposition. Real and imaginary part is standard, but not typically used. And if you do this, then you find that if you just take the imaginary part, which is a real field, this fulfills the action I've shown you before. Okay, so there are some parts in there. You don't take the full phononic field, but only the imaginary part. This one fulfills this kind of action we want to implement. Now, the phi1 is the conjugate field. This is also good to have and also accessible experimentally. Okay, so now how do you do this? I should go faster. How do you probe? You have curved space. You throw something and you see it bends, right? Light, you send, it's bent. What's the analog, classical analog for a quantum field? It's a wave packet. A wave packet is the most classical object. You send it off and see what happens. And if you do this, then you see if you do this curved space, actually it expands. Actually not so easy to see that this is curved. But then if you analyze it, And you can read more details in this article down here. If you analyze it, you find, yeah, indeed, it behaves like if the metric is curved. Now, if the metric is curved, you might wonder, can you not also produce the other metric, not a hyperbolic metric, but a spherical metric? Okay, now what we have to do is we have to make the sound velocity faster at the edges and slower in the middle. But this you can do. We have these digital mirror devices, micro mirror devices. You can make arbitrary potentials for the atoms. And then if you fill them, you have arbitrary distributions of densities. And with that, you can also produce spherical space. So essentially, you have control of this curvature in your experiment. Okay, and we can probe this with the wave packets. So now at the end, the question is, what's quantum there? It's a wave packet. It's very classical. Where's the quantum part? The quantum part comes in if you change the scale factor. So if you rip the space apart and ask, how does the field react? And everybody would say, well, if you rip the space apart, then you have to get some excitations on top of the field. That's called particle production in this community. And it's also something which is this explanation for this WMAP structure, or for the microwave background structure measured by WMAP. And that's actually you can do, but you don't expand your system in real space, you expand your ruler. And you do this by changing the scattering length, which you can do with potassium very nicely. So actually you take a stationary system, you change your scattering length, i.e. your ruler, and then what you get is a similar thing as expansion. And what you get then there is these kind of pictures. So the universe with quantum fluctuations at the beginning, and then you rip it apart and you see that you get structures. You get here bigger structures. And the good thing about this universe is it's not a real universe, it's just an expanding space-time for a scalar field, but it can do this more often than once. And so we can do statistics of the system, and that's what we do, and all the details you can read in this paper here, soon also published. And what we find is actually that this first approach for theory is not confirmed. This was very funny to experience. I can talk about this later on, and don't spoil the main result of this paper. Okay, with that, I'm at the end. So I've shown you that actually these atomic systems have different aspects. One is really using them and taking all our techniques. I think there's big potential, taking our techniques and transfer this to other people, using them then later on. And this only works if both are interested in. And it was in our case in Heidelberg a lucky situation that Werner had all this experience in this environmental physics part. The other things, what I will show you here are recent results, and it's always connected to the regime we're working in is this quantum, I call it quantum field setting, i.e. we are not single particle resolved measurements, but we have objects which are described by fields, and we look at the fluctuations of them, and we're always interested in entanglement, and that's actually the next plan for this expanding universe is see horizon physics and see consequences for entanglement. With that, I'm sorry for being 10 minutes late, and hope there's still some time for a discussion. Thank you very much.
Thanks a lot for the very nice talk. And of course, we have time for discussion. So are there questions already? Anybody here? Or also people in Zoom can just speak up. Yeah, I see a question. Professor Hensch, please.
Yeah, first of all, thank you for very spirited talk regarding the cosmology. I always have trouble to understand what is even meant by time in the very beginning. How would you measure it?
Yeah, well, it's a tough question and I have no answer. I'm sorry, there's no competence on my side to say something about this.
Some people argue that time is an emergent phenomenon. It doesn't make sense to talk about time before the Big Bang and also in the very beginning. Probably it doesn't make sense because I would need to know how should I measure it.
Yeah, you know, you need objects which have a time kind of constant somehow, I guess. But here it's a little bit different. I mean, I'm sorry, I have no competence here. But one question would be a little bit, suppose there is something in front of this universe and you have this metric kind of picture and you can go through a sort of bounds. Yeah? You can ask, actually, if there's time, there's no time in between. Okay, nothing will survive from what was before. But if there's something, there might be some information what happened before. And this is something we could look at on a model system. This is not the universe, yeah, but this is a natural question. If you have these kind of extreme situations of metrics, which actually changes on the scale of particles, and you go through something singularly like this, what happens afterwards is something we could ask and also kind of translate into an experimental sequence. If the answer then at the end is relevant to real world, I have my doubts because many things break down in the approximations necessary to have this picture. Yeah, but yeah, I'm sorry. There's not more I can say. Yeah.
I think the first.
No, this is on a, okay, there's now, there are different things, yeah. One thing here was very clear, the original question was very local one because the oxygen minimum zone, which is there. This other thing is now really like there are big campaigns now. So we get samples and we are involved in big campaigns where they get the samples and you have to take special samples for this argon, which is not the natural kind of probing. And we get them, they're EC projects, we actually are their collaborators, where they want to get samples also from the Antarctica circle. And as you say, local information is good, but it's not really relevant if you want to understand some flow or some changes in time or the bigger structure in the ocean. Exactly. For example, I mean, one thing what made me kind of happy and somehow seeing that this is relevant is that the simulators now take Argon into account. They put this in their models because you cannot back calculate. So essentially having flow and seeing where it goes, actually, if you take tracers too in simulations and they put this Argon tracer in. The other thing is that, as I said, there are lots of campaigns now where we always get kind of asked if you want to join. And that means we get a certain number of samples and they take their specific positions where they think it's interesting for them. For example, in North Atlantic, we have a campaign where there's a big ridge. And the obvious question is what goes over, what goes down? Is the flow going down and how much? But these are not questions I appreciate and learn, but I cannot give input there. But it's a very exciting thing. And it's amazing how I was always naive. I thought we can do lots of calculations and simulations, like on big scales, but this is not true.
Okay, Markus, also concerning this first part. So, so how do you settle on Argon, or is this sort of the obvious best choice, or are there also other species that you could use that at different timescales, I imagine?
Yeah, Argon is, it's not, we didn't invent Argon. Argon was kind of in the late 60s found as a very interesting tracer. And for tracers in this kind of context, we would like to have inert tracers, i.e. not interacting chemically. This is for C14 extremely difficult. C14 in this body is nice, yeah, because it's contained. But in the ocean, if you want to do C14, you have everything which falls down and it's not kind of local and it has chemical reactions. So that was that's actually a lucky situation that these noble gases have this property. That Argon 39 was good at that time. And actually first dating was with glaciers, actually. They took thousands of liters of glacier ice because they knew how old this is and then did low level counting. So you count the decays. It also takes like half a year, but then you have enough, or 2 months to get enough statistics, and then you can make an estimate. And from that point of view, Argon was a very interesting tracer because it was filling the years 600 to 100 or 800 to 100. And if you look at the other tracers, which are typically C14, it's not so good in this range. Actually, it starts for 1000 and older. And if you look for other things like tritium, tritium was produced by bombs. This is very good for very young ones. So essentially, one thing that was also like I was introduced to the dating gap, and the dating gap is, guess what, in this range where Argon fills it. So one gives this talk also with this kind of tracers, and then there's a gap, and then Argon fits in here. So that's why Argon was interesting and has some resonance because it's the right time scale. So it's Not everybody is interested, but these ocean people, this is exactly the time scale. So if you think about the ocean flow, it goes 1,000 years from North Pole to the South America. That's the estimate. So everything is in this ballpark, and that's why Argon is interesting. Inert, and the only thing was, and I didn't mention this, that this low-level counting relies thousands of liters. Because if something decays, it's rare, and it decays not very strongly, you have to have enough that you see something. And that was 1,000 liters, the scale. And they did this also in the ocean already. But 1,000 liters, you don't do a line like what we did. Yeah, you go for 1 point and measure it, and you're happy, and you have some information. It's cool. But if you want to get this full resolution, then you have to go to smaller volumes. And that actually was the main step, having smaller volumes. And also actually we are now faster than them because they have to wait. And our sample takes 1 day.
And just to be clear, what you measure is the last time, the time since the last time the water was in contact with atmosphere. So if the water like circulates and is near the ocean surface, that also basically resets the time.
Exactly. Yeah. Exactly. And this is also what I learned. Sorry if I tell you what I learned, but I found it is like, you know, environmental systems, they are very complicated typically. Yeah, if you're in the upper ocean, then it mixes everything, and there is no hope that you can get with this something. You have to go to a situation where it's relatively clean. And a typical example is, how can you take from 3 rings the temperature? Didn't you ever ask you, if you see this nice curve, temperature versus time, those 150 years, there is this nice grow up, not grow up, which is measured, and everything else is 3 rings. So how do we estimate from 3 rings temperature? And I was this tree, why does this tree know about temperature? And obviously it does not know. It knows, but it knows many things more. You have to go to trees which are extremely special, at special places where the growth is defined by temperature, not by water, not by anything else, but there are few trees like this, but they exist. And that's somehow how you have to go about. You have to look for situations where you can say something, and these mixing zones themselves are extremely interesting, but then this is maybe not the best approach.
Are there any more questions here or online? There's one.
Maybe this is a follow-up question to the one before. So how do you know that the water hasn't mixed with younger water and you just get an average age?
Super cool. Exactly right. If you take one number, how can you tell? And that's why these results, and that was quick there, is not one number. There are other traces, CFCs, which you additionally take, and then you make a consistency check, assuming a certain transit distribution, transit time distribution. So you have to assume something. That's the more if you have only 2 numbers, but you have something where you say, okay, in this area it could come via diffusion or via convection, then you can maybe boil it down to a distribution function of a certain shape, which has a width and a mean. And then you try to understand the data given this prior. And that's how you find then this age. So actually what we found was not the absolute age, but the age distribution was shifted to the younger than it was expected before. And that's why you have to have more. Yeah, it's also the same. If 1 number is not enough, 2 is not enough, you have to get as many numbers as possible. And then you can constrain it more and more to something which has certain reality. And in this case, it was a distribution function. We could bound that the width was actually larger than expected. And that is only, with the 2 data, this was the only consistent solution. As I also like, I have all the people here with the quantum technology and all this knowledge in atomic physics. There's lots of things which can be done there. If they have our techniques, I guess they get other possibilities. I find this extremely exciting.
Do we have another question online, maybe? Yes, please.
So here we start from the hypothesis also, so about the Argon part, that we have the atmosphere abundance of the isotropic Argon fixed, but is it neglectable? I guess it will fluctuate also with how high are the clouds, and like can we neglect the variation of this? Or do we...
Yeah, very good question. So I think the clouds are maybe not the most important part because it's in the upper atmosphere, but it's the influx from the sun which is time dependent. And we notice for C14, there are big fluctuations. And for C14 in the last 500 years, you have to take this into account. And you have certain times you cannot uniquely find because the influx are either low and it's old, or the influx are high and it's even older. The good thing about this argon is that it's in the atmosphere. So actually everything is redistributed and it's averaged. And the other thing is all the timescales here is not like today it goes into the water and then it's there. There's an exchange on the scale of a year or so, which you average. So the averaging is also on your side. But there were recent kind of estimation coming also from trees, where you also can make the C14 estimation and the influx of the sun, and then make a back calculation of what it means for the argon-39 production, and it's in the range of 10%. So there is some variation of 10% over the last 1,000 years. And at the moment, we are not at this level. And also environmental systems very often are not so critical in time on 10% level. It's more like, is it 300 or 100? And that information you can get. But it's a very good question. And I think one thing I would like to do is get old air. How do you get old air? And I was addressed by somebody who wants to get the ocean temperature of last century or 19th century. And you get old air, you can buy it on eBay. It's like glass spheres of the fishermen. They had glass spheres to hold their nets up. And actually, this is enclosed air. So now, and they know how old it is because there's a stamp. And this is only the last 200 years. So for the other parts, it will be hard. But then he said, well, alcohol is also extremely old, and this alcohol things you measure the alcohol content is also a vessel, which is kind of sealed. But yeah, at the moment, I think the estimation is the thing we have to live with, and the estimations are about 10% variation for the last 1,000 years.
Okay, thank you.
Another question here or online? If this is not the case, then let's thank Markus again.